An unexpected emission has begun to draw attention toward Mount Vesuvius, a volcano long studied yet still capable of producing observations that challenge established understanding. What exactly is emerging from one of the world's most closely monitored volcanic systems? Why are measurements taken near its summit showing unusual signatures compared to surrounding regions? And how does a volcano with centuries of documented behavior continue to reveal features that resist simple explanation? Situated east of Naples, Mount Vesuvius rises to an elevation of about 1,281 meters, or roughly 4,200 feet above sea level. It is part of the Campanian volcanic arc, a region shaped by the ongoing interaction between the African plate and the Eurasian plate. This tectonic convergence has sustained volcanic activity for hundreds of thousands of years, feeding magma reservoirs beneath the surface and periodically releasing energy through eruptions, gas emissions, and thermal anomalies. Recent observations, however, have highlighted a different kind of phenomenon. Instruments positioned near the summit crater have recorded a persistent release of a substance that does not conform neatly to the expected categories of gas, ash, or lava. It is not visibly explosive, nor does it behave like typical fumarolic emissions that consist largely of steam mixed with sulfur compounds. Instead, the material appears as a diffuse yet measurable output, detectable through radiometric equipment rather than visual inspection alone. Radiation counters deployed across the volcanic edifice have shown a noticeable contrast between baseline levels in surrounding areas and those recorded near the summit. In nearby lowland regions, typical background radiation ranges from approximately 6 to 16 counts per second. Yet, at higher elevations, especially within and around the crater zone, measurements have consistently reached between 58 and 62 counts per second. That difference, while not immediately hazardous, is significant enough to prompt closer examination. The substance associated with this emission is not an imported contaminant or a byproduct of industrial activity. Instead, it originates from the volcano itself, embedded within the chemistry of its rocks and the gases released from its interior. The elevated readings are linked to naturally occurring radioactive elements, particularly uranium and thorium, along with isotopes formed through their decay processes. These elements are present in many parts of the Earth's crust, but their concentrations at Mount Vesuvius are notably higher than regional averages. Typical crustal compositions contain uranium at around 2.4 parts per million and thorium at about 7.8 parts per million. By comparison, samples of Vesuvian lava have shown concentrations closer to 6 parts per million for uranium and approximately 19 parts per million for thorium. This enrichment suggests that the magma feeding the volcano has undergone processes that selectively concentrate these elements rather than distributing them evenly. One of the key mechanisms behind this concentration lies in the behavior of what geologists classify as incompatible elements. During the melting of mantle rocks, certain elements do not fit easily into the crystalline structures of forming minerals. Instead of becoming locked within solid phases, they remain in the liquid portion of the melt. As magma evolves and rises, these elements become increasingly concentrated, leading to higher-than-average abundances in volcanic products. The tectonic setting beneath Mount Vesuvius plays a critical role in this process. As the African plate descends beneath the Eurasian plate, it carries with it sediments and oceanic crust that have accumulated over millions of years. These materials often contain trace amounts of uranium and thorium derived from both continental sources and marine deposition. When subjected to high pressures and temperatures, the subducting slab releases fluids into the overlying mantle wedge, lowering the melting point and generating magma. During this partial melting, incompatible elements such as uranium and thorium preferentially enter the melt. Over time, repeated cycles of melting and differentiation can amplify their concentration. The resulting magma, enriched in these elements, eventually ascends toward the surface, feeding volcanic activity and contributing to the chemical signature observed at the summit. Another factor influencing the observed phenomenon is the release of radon gas. Radon is a radioactive noble gas produced during the decay of uranium. One of its isotopes, radon-222, is particularly significant due to its ability to migrate through porous rock and escape into the atmosphere. At Mount Vesuvius, fumarolic activity provides pathways for this gas to reach the surface. The summit crater, characterized by fractures and vents, serves as a focal point for degassing processes. Measurements indicate that radon emissions are more concentrated near these active zones, contributing to the elevated radiation counts recorded by monitoring instruments. The gas itself is invisible and odorless, making it difficult to detect without specialized equipment. Its presence, however, is consistent with the decay chains of uranium and thorium, linking the observed emissions to the underlying geochemical processes. Despite the elevated readings, the levels detected remain below thresholds associated with significant health risks under typical exposure conditions. For comparison, natural background radiation varies widely across the globe, with some regions exhibiting higher baseline levels due to local geology. The values recorded at Mount Vesuvius, while above regional norms, do not reach levels that would necessitate immediate concern for short-term exposure. What makes this development noteworthy is not the presence of radiation itself, but the way in which it is being expressed. The emission behaves like a persistent output, almost as if the volcano is releasing a continuous stream of measurable energy rather than sporadic bursts associated with eruptions. This steady release raises questions about the internal state of the magma system and the dynamics of gas transport within the volcanic structure. Historical records of the eruption of Mount Vesuvius in 79 AD have documented the volcano's capacity for sudden and devastating activity. That event buried the nearby cities of Pompeii and Herculaneum under layers of ash and pyroclastic material, preserving them for centuries. Since then, the volcano has remained active, with its most recent eruption occurring in 1944. Continuous monitoring has become a priority, given the dense population living in the surrounding region. Modern surveillance systems include seismic networks, gas analyzers, satellite observations, and ground-based sensors. These tools provide a comprehensive picture of the volcano's behavior, allowing for the detection of subtle changes that might precede more significant activity. The recent identification of this unusual emission adds another layer to that monitoring effort, highlighting the complexity of volcanic systems and the need for ongoing observation. The substance itself does not appear as a visible plume in the way that ash clouds or steam columns do. Instead, it is defined by its measurable properties, radiation counts, gas composition, and spatial distribution. This makes it less conspicuous to casual observers, but highly significant to those analyzing the data. The contrast between its invisibility and its detectability underscores the importance of instrumentation in modern volcanology. Geochemical analyses of rock samples and gas emissions continue to provide insight into the processes at work. By examining isotopic ratios and elemental concentrations, researchers can trace the origins of the materials being released and reconstruct the pathways they have taken from deep within the Earth. These studies suggest that the enrichment of uranium and thorium is not uniform throughout the volcano, but varies depending on the source and evolution of the magma. The role of hydrothermal systems also comes into focus. Beneath the surface, circulating fluids interact with hot rocks and magma, altering their composition and facilitating the transport of gases. These interactions can create localized zones where certain elements become concentrated, further influencing the characteristics of emissions at the surface. In the case of Mount Vesuvius, the interplay between magma, fluids and rock appears to be a key factor in producing the observed phenomenon. Patterns emerging from continued monitoring around Mount Vesuvius suggest that the unusual emission is not a brief anomaly, but part of a sustained process tied to the volcano's internal structure. Data collected over extended observation periods indicate that the elevated readings fluctuate within a narrow range rather than spiking erratically. This consistency points toward a stable mechanism of release, one that is governed by the steady movement of gases and the slow evolution of magma beneath the surface. At elevations approaching 1,200 meters or close to 4,000 feet, the summit crater acts as a natural conduit for subsurface activity. Fractures and vents provide pathways for gases to migrate upward, allowing volatile components to escape from deeper levels, where pressure and temperature conditions differ significantly. These conduits are not static. They evolve over time as rocks expand, contract and fracture under thermal and mechanical stress. Such changes can subtly alter the rate at which gases are released, influencing the intensity of the measured emissions without producing visible surface disturbances. The distribution of the radioactive signal across the volcano reveals another important detail. Measurements taken along the cone slopes show a gradual decrease in counts per second as distance from the summit increases. At mid-elevations, values fall closer to regional background levels, reinforcing the idea that the source of the emission is concentrated within the upper section of the volcanic structure. This spatial gradient aligns with the known pattern of fumarolic activity, which is most active near the crater where gas escape is most direct. The role of radon gas remains central to interpreting the phenomenon. As a product of uranium decay, radon forms continuously within rocks that contain trace amounts of radioactive elements. Its gaseous state allows it to move through microscopic pores and fractures, eventually reaching the surface. Once released, it disperses rapidly into the atmosphere, but near its point of exit, concentrations can remain elevated long enough to be detected by sensitive instruments. At Mount Vesuvius, the persistent emission of radon contributes significantly to the recorded radiation levels, effectively acting as a tracer for deeper geochemical processes. Another aspect under close examination is the relationship between temperature variations and emission intensity. Thermal imaging of the summit region has identified localized zones where surface temperatures exceed surrounding areas by several degrees. These anomalies, while modest in scale, correspond closely with points of elevated gas release. Warmer areas tend to coincide with active vents, suggesting that heat flow and gas migration are linked components of the same underlying system. The heat facilitates the movement of gases, reducing their density and allowing them to rise more efficiently through the rocks. The composition of the emitted material, though dominated by invisible gases, also includes minute particulates carried upward from the volcanic interior. These particles are often too fine to be seen without specialized equipment, yet they can carry measurable amounts of radioactive elements. When deposited near the summit, they contribute to the overall radiation signature detected in the area. Over time, such accumulation may create localized zones of slightly higher radioactivity, further distinguishing the crater environment from surrounding regions. Geophysical models of Mount Vesuvius suggest that the magma chamber beneath the volcano is not a single huge reservoir, but a complex network of interconnected pockets. These pockets can vary in depth, composition and temperature, creating a dynamic system in which magma and gases interact continuously. As gases separate from the molten material, they accumulate in pressure zones until they find pathways to escape. The steady emission observed at the surface implies that these pathways remain open and active, allowing gases to vent without building up to explosive pressures. Seismic data provide additional context for understanding this behavior. Instruments placed around the volcano detect low levels of background seismicity, characterized by small frequent tremors rather than large isolated events. These microseismic signals are often associated with the movement of fluids and gases inside the crust, rather than the fracturing of rock on a large scale. Their presence supports the idea that the volcano is undergoing continuous internal adjustment, with gases migrating through established channels rather than forcing new pathways. Comparisons with other volcanic systems highlight the distinctiveness of the current observations. While elevated natural radioactivity has been documented in certain regions, the combination of persistent emission, localized concentration and clear connection with volcanic degassing is less common. Many volcanoes release large quantities of water vapor, carbon dioxide and sulfur dioxide, but fewer exhibit a measurable release of radioactive gases at levels that stand out so clearly against regional backgrounds. This makes Mount Vesuvius an important case for studying the intersection of geochemistry and volcanic activity. Environmental monitoring in the surrounding area has not detected significant changes beyond the immediate vicinity of the summit. Air samples collected at lower elevations show radiation levels consistent with natural background conditions, indicating that the emission disperses effectively as it moves away from its source. This dispersion reduces the potential for accumulation in populated areas, a critical factor given the proximity of urban centres such as Naples, located roughly 9 kilometres or about 5.5 miles from the volcano. Long-term datasets also reveal that similar, though less pronounced patterns have been recorded in previous years. Historical measurements indicate occasional increases in summit radiation levels, often linked to periods of heightened fumarolic activity. What distinguishes the current situation is the clarity and consistency of the signal, made possible by advances in instrumentation and continuous monitoring techniques. Modern sensors can detect subtle variations with greater precision, allowing patterns to emerge that might previously have gone unnoticed. The chemistry of the emitted gases provides further insight into their origin. Alongside radon, traces of helium isotopes have been detected, offering clues about the depth from which the gases are rising. Certain helium ratios are associated with mantle-derived sources, suggesting that at least part of the gas originates from deep within the Earth rather than from shallow crustal processes alone. This connection reinforces the idea that the observed emission is linked to the broader dynamics of magma generation and movement beneath the volcano. Attention is also being directed toward the influence of atmospheric conditions on the measurements. Wind patterns, humidity and temperature gradients can all affect how gases disperse after reaching the surface. On days with low wind speeds, concentrations near the summit may remain elevated for longer periods, resulting in higher recorded counts. Conversely, stronger winds can dilute the emission more rapidly, reducing localized readings without altering the underlying rate of release. Accounting for these variables is essential for interpreting the data accurately. The stability of the emission over time suggests that it is not driven by a single transient event, but by a continuous supply of gas from depth. This steady-state condition indicates a balance between gas generation and release, where the system is able to vent efficiently without accumulating excess pressure. Such behavior contrasts with scenarios that lead to explosive eruptions, where gases become trapped and pressure builds until it is released suddenly. At present, the data from Mount Vesuvius do not show signs of such pressure accumulation. Nevertheless, the presence of this unusual emission underscores the importance of maintaining comprehensive monitoring systems. Even stable processes can evolve over time, and changes in gas composition, release rate or spatial distribution may provide early indications of shifts within the volcanic system. Continuous observation allows for the detection of these changes at an early stage, supporting more accurate assessments of volcanic activity. The interaction between geological processes and measurable surface phenomena remains a central focus of ongoing study. Each data point contributes to a more detailed picture of how elements move from deep inside the Earth to the surface environment. At Mount Vesuvius, the current observations highlight a pathway that is both subtle and persistent, revealing aspects of volcanic behavior that extend beyond the more visible expressions of eruptions and lava flows. As the dataset continues to grow, patterns may become clearer, allowing for more refined interpretations of the processes involved. The integration of geochemical, geophysical and environmental data provides a comprehensive framework for understanding the phenomenon, ensuring that each aspect is considered in relation to the others. This holistic approach is essential for capturing the complexity of volcanic systems, where multiple factors interact simultaneously. The ongoing emission does not redefine the overall behavior of Mount Vesuvius, but it adds a layer of detail that enriches the understanding of its internal workings. It demonstrates how even well-documented volcanoes can present new features when observed with sufficient precision and continuity. By examining these features in detail, it becomes possible to refine models of magma dynamics, gas transport, and elemental distribution, contributing to a broader understanding of volcanic processes worldwide. For viewers following developments like this, staying informed is key. If you found this breakdown insightful, make sure to like, share and subscribe. And don't forget to tap that hype icon to help this reach a wider audience.